Hello again. I'm back. And I'm only back because I do have the paper, and I will, I guess, keep making these videos as long as I keep getting these papers. A little preamble before, I guess, I start. IB's kind of locked down on security. I think they spent a good amount of money hunting down, I think there are a couple of students somewhere in the world that leaked the papers. And that's also why this is a little bit late. Also, I don't have paper 3 just because my source could not get me paper 3 this year. However, they did tell me a couple of things. One, for some reason, paper 3 has historically been kind of a poor performing paper. So what they've done is this year they've extended the time allowed to write it, and also they made it easier. Like, as a personal opinion, I think it was the easiest one, and it's always been the easiest one. But it does require like a certain type of approach, I guess, to do it well, that maybe a lot of students don't have. But I've heard that it was super easy this year, so maybe I don't need to go through it. And also, as usual, this, aside from me just like seeing the questions as I've copied and pasted them into this OneNote, I don't have the mark scheme. I have not done these questions yet. I have not taken a good look at these questions yet. And also, I'm going to be even more nerfed because it's been like 2 years since I've done any sort of math at an IB level. So definitely expect things to be wrong. Please leave, I guess, a timestamp and a comment if you find something wrong. And yeah, it's my first run through this, and I guess I'll just get started. It's paper 1, and in typical HL fashion, there's probably going to be like 5 to 6 SL questions, and these are going to be on the SL paper. So if you are here for the SL, you know, just skip around and find out which ones are yours. But okay, let's see. Pretty classic rewrite a question in terms of P and Q using log properties. So here's log base 10 of 24, and we would like to write 24 in terms of 2 and 3. So that's pretty straightforward, right? Oh my god, I haven't used the tablet in so long. 24 can be written as 2 times 2 times 2 times 3. Yeah. You know what, let's just do it this way. 2 times 2 times 2 is 8 times 3 is 24. You can write this as a power and then use like a different log property, but let's just write it like this. This is a product, so we can change this into addition. Sure, keep it simple. And again, there's lots of ways you can do this. And now everything is written in terms of log base 10 of 2 and log base 10 of 3. So we can just replace all of these with p's. So this is p plus p plus p. And then we can write that as q. And then collect our p's. So for a, this is what, 3p plus q? 3 marks. Easy peasy. And then, let's see, we have this. It's log base 3. So what we're going to need to do first is change it into log base 10 using our change of base formula. So log base 10 of 8, log base 10 of 3. Okay, and then the bottom is easy. That's literally just q. And then 8, we will need to write into some sort of power of 2 or multiplication of 2 and 3, and that's pretty straightforward. 8 is 2 to the power of 3. And then, so this one, I'm using the exponent. You can use your log rule, log law, to write the exponent as a coefficient. And I'm showing all my work. Honestly, you don't need to show all your work. You could probably just skip from here to the actual answer. So Q 3p over Q. Easy peasy. And you know, in terms of test taking strategies, 1 mark should be how many minutes you spend. So this question, it recommends 5 minutes. To be honest, all of these short answer questions, I told my old students, because I don't teach IB anymore, if you cannot do a short answer question right away, then you should just skip it and leave it for later. Like, if you think you have to think about it, like, leave it for later. Like, I know it says 5 marks, but honestly, it should take you like 2 minutes to do. So go through all the ones that you can do right away first, go back afterwards and spend a little bit more time on the other ones. Okay, question 2. We got this graph. Sure. Write down the value of f of -3. So then, straightforward, this is your x. They want you to find what's the y value at -3. So at -3, here's your graph right here. Your y value is -1. -1. Okay, state the domain of the inverse. So the inverse switches the domain and the range because it takes all of your y values as your outputs, because normally it's like x is in, and then it gives you out your y's. Your inverse takes the old outputs as an input, and then it outputs the x. I guess as a picture, it looks like this. Right, this is f, y is the inverse, the inverse takes y and brings it back to x. Okay, so this should be the range of f, the original. Your range is from 5 to -3. So your domain is from -3 to 5. Right, this is the highest value for y, and then this is the lowest value of y, so then that's your range. Your graph is all the values in between. Okay, and then find the value of x that satisfies this. So inverse of stuff equals -3. Okay, so keep in mind that the output of your inverse, the output of the inverse is the original input for the original function. So what this is saying, right, is that this is the original input, this is the original output, otherwise known as the x and the y. So if my original input is -3, I need to find out what my original output is, because that's going to be 2x minus 7. I think we already did that here, right? If my original function's input is -3, I get an output or a y value of -1. So what that means is that this thing is -1. So 2x minus 7 is -1, because I know that if I put in -1, I should get -3. Because if I put in -3 in the original, I get -1. Okay, and then you go find x. What the heck is this? So this goes there, so like 3, I guess. Yeah, that makes sense. Okie dokie. Next one. we gotta solve this trig equation. Looks fun. There is a double angle, so you know right away you should be using one of your double angle identities. If you take a look at the options you have, so here's my formula sheet. Trigonometry. So double angle has three options. We have this one where you have cosine squared and sine squared. You have the one that has just cosine squared, and then you have the one that's just sine squared. When you're solving an equation, a trig equation, you should try to keep them all the same ratio. So this one is already a cosine, so that means that I would be picking the one that only has cosine in it, this one here. So that, what is that, 2? Okay, so we're going to use our double angle identity. We're going to change the cosine 2 into 2 cosine squared theta minus 1 minus 5 cosine theta plus 2 equals 0. Okay, and then we're going to simplify this, so this becomes 4 cosine squared theta minus 5 cosine theta, and then that's it. Okay, they were nice to you. Okay, and then we want to solve this. You can treat this like a quadratic, essentially. And, you know, for people watching at an HL level, like, this is pretty straightforward because this is an SL level question, but of course, I got to do this for the SL kids as well. Right, you don't have to do this, but I'm like stating it explicitly. I would never do this. But if you let cosine be x, then this becomes 4x squared minus 5x equals 0. And you need to be able to see this, of course, and then that's why I'm writing it here, so that you can see it a little bit more explicitly. But we are solving for x. We're solving for cosine. So what would you do? You would factor out the x. So same thing, right? We would factor out the cosine. So you would get 4 cosine theta minus 5 equals 0. And then, right, like you would literally factor out the x. Hello? Am I not allowed to change color right now? Okay, I can't change color, but hopefully you can see that, like, you're literally just factoring out the x. And then you're solving for x or solving for cosine. Okay, so from here, you have two options. Either cosine is 0, or the other factor, the 4 cosine theta minus 5 theta is 0. Okay. Now, the second one's easy, because if you were to solve for cosine, you're going to get 5 over 4. 5 over 4 is greater than 1. That means that we don't have a solution for this one. No solution. Cosine is between 1 and -1. So if this just ends up being more than 1, there's no solution for this part. So we have a solution for just the first part, cosine being 0. I guess I'll use bullet points or something. Okay, for this one, this should just come from memory. You should know where cosine is 0. Ironically, I'm trying to remember. But I believe it's pi over 2 and 3 pi over 2. And then just to finish off the question, they do tell you a specific domain. We are only going to accept angles that are between pi and 2 pi over 2. So we only have one answer, this one. This one, the first one, is not part of the domain in the question. How am I doing for time? 15 minutes? kind of slow, but I am explaining this, of course. Okay, second one, we got a parabola and a line. They are going to intersect somewhere. Okay, easy enough. Intersections mean that their y values are equal, so we can just equate the two. And then we're just going to rearrange this, and it will turn into part A. So everything goes to one side. Plus 3 equals 0. And then, right, you factor out the x here. Can you guys see my mouse? I can't see my mouse. Uh-oh. I've been using my mouse to point, but I don't see it on my recording thing. Okay, we factor out the x, and then these two get collected together, and then you get part A. Okay, part B. Hence, find the values of m, which this line is tangent to the curve. So the word hence in an IB paper for math basically saying you have to use the previous part. So that's good and bad. Mostly good, because you don't need to understand how to get the second part or the first part to do the second part. It says hence. That means just use what they give you. If you couldn't get this for some reason, you can still use it for part B, and you can still get your marks, full marks for part B. Okay, so we want to find out when this is tangent to the curve. There's lots of ways to do this. You can use calculus, you can, but basically what they're saying is that it only intersects once. In other words, there's only one solution. This is still a quadratic, part A. If we know that there's only one solution, there's only one intersection, we can just use the discriminant in the quadratic formula, the 4b squared, or the b squared minus 4ac. And then if there's only one solution, that means that your discriminant is equal to 0. Okay, what's your a, b, and c? A is 1. Here's your b. Careful with the negative. And then there's your c. Okay, so I'm just going to do that. So b squared negative m plus 1 squared minus 4 times a times c. Okay, so then this is going to be m plus 1 squared minus 8. Okay, and then this needs to equal to 0. Okay, I just squared the negative. I don't need to expand this because I'm solving for m. And this is already just one term of m. And then this we can just keep solving. So m plus 1 squared is equal to 8. That means that m plus 1 is plus or minus the root of 8. So m is negative 1 plus or minus the root of 8. And then I don't remember if they ask you to simplify your surds or your radicals. If you do, then do it. If you don't, then you can just leave it. I mean, this isn't a hard one to simplify because it's 4 times 2, and then the root of 4 is 2. Okay, kind of an ugly answer for a paper 1, but still within reason. Okay, question 5. We have two normal random variables normally distributed. X has a mean of 7, standard deviation of a. Y has a mean of 19, and then the same standard deviation. Okay. So before I start, I do like to draw these. Just helps me see things. So x is here with a 7, and then y is exactly the same standard deviation, so the same like width to the bell curve. However, it has a different average. Okay, find b such that x greater than b is the same. The probability of x being greater than b is the same as the probability of y being greater than 22. Okay, easy peasy. So for y being greater than 22, right, we want to find the b value that has the same probability or the same area under the curve. But because they have the same standard deviation, hopefully I've been saying standard deviation, that means that literally like from 7 to 19 is like, all right, let's go backwards. From 19 to 7, that's a difference of what, minus 12, I want to say. And so they have the exact same probabilities in the exact same places. And then all we got to do is do the same thing, right? Take 22 and subtract 12. So what is b? B is 10. Right? Same shape, same standard deviation. So we just find the difference in their means. And then go from there. Write down the approximate value of p probability of x being between 7 minus a and 7 plus a. Okay, a is our standard distribution. So this is literally saying within one standard distribution. So this is something, again, that comes from your memory. Right, you got x, this is 7. And then within a single a, one standard distribution. This is a percentage that you should know. I forget what IB says. I think it's like 68%. So 0.68, something like that. I could Google it, but I'm not gonna. Right, this is one standard deviation. Okay, and then I forgot to mention this, but things that are worth 1 mark, they are that easy. I was gonna say it earlier because there's a 1 mark one, these ones. So don't think about it too hard. Okay, part C. Given that the standard deviation is 3, calculate the approximate value of p of y greater than 22. Okay, so here's y, here's 19, 22, I'll use red. And we want to find this area or probability. And then again, because a is 3, this is one standard distribution away. That's a sigma. Therefore, we can use our things to figure out what this area is. Shoot. I think it's like... Okay, so this is within, again, one standard distribution is 68%. That means that the tails are the other part of 100%, which is like 22, 32. That's a little misleading. Okay, 32, and then divide that by 2, so each one is like 16%? Something like this. Okay, and then we want essentially these two together. So add them up. P of y being less than 22 is whatever this is, like 84%. 0.16 plus 0.68. Okay. And then we're on question 6, so this is like the last SL or the first HL question. Oblique asymptote, so this is HL. Okay, what do we got? Sure. Graph. On the following grid, sketch the modulus absolute value, clearly indicating any asymptotes. Fantastic. Okay, absolute value is straightforward, or the modulus. It's essentially saying take any y values on the original graph and then turn them positive, which means that they will flip over the x-axis. So like this whole section here is gonna flip, including the asymptote. Okay, we gotta be a little bit accurate because they want us to clearly indicate asymptotes. What is the asymptote? 5x plus 5. Okay. And then what is the scale, dude? 2 and 1 is here. Oh my god, dude. Okay. Okay, let's just sketch the part that doesn't change, the invariant part. So that would be anything that's above the x-axis. So this part here. This is going to stay the same. So the line goes... Why would they give you this scale? Oh my god, dude. Okay. So it goes up 10 for every 2. So here. Okay, boop, boop, boop. You would obviously use a ruler. Boop, boop, boop. So here's your asymptotes. And then the original one, oh, that's at 0.5. Okay, sketch this thing. Okay, and then the asymptote will get reflected, and then it goes this way. Again, try to make it accurate. I don't care because of this scale is frustrating me. Why would they do this in 2s and this in 0.5? But whatever, it is what it is. Okay, and then this part here gets reflected upwards, and let's see how accurate they want it. Sketch it. Okay, point A is at -5/2, so 2.5. So 2.5. Like here? Sure. Good enough. There you go. 4 marks though. Okay, on the following grid, sketch the reciprocal. Okay. Intercepts with the axes. Okay. Let me erase this stuff. Okay, so next up, we're going to take the reciprocal of this, which means that the y values on the reciprocal graph are 15 divided by the y values on the original graph. So they did give you specifically two y values. They have -5/2 right here. And this one here, 15/2. Okay, so I'm gonna start with those ones. We're gonna take 15 and divide it by these, right? Take 15 and divide by those y values. So this should be straightforward. 15 divided by 15/2. This is just 2. 15 divided by -5/2. What the heck is this? Like -2/3 or something? Ugh, fraction division. Or is it 6? I think it's 6. -6. Okay. So they are at an x value of -1 and on the y-axis. So dot here, dot here. Okay. Then we have our third coordinate, which is where the original vertical asymptote was. Vertical asymptotes happen because there's a division by 0 here. So your y value is like something divided by 0 here. So then, if we were to take the reciprocal at the asymptote, so 15 divided by something divided by 0, this becomes 15 times 0 divided by something. So, and this something is non-zero maybe, but whatever. This is just 0. We have an x-intercept where there's a vertical asymptote. This looks weird, but okay. Okay. Okay, let me just check this one. This one looks okay. 15 times -2/5. Oh no, it is -6. Okay. Okay, now we sketch out the rest. As you can see, from this point, the y values get larger as we go to the right and as we go towards where our original asymptote was. If our y value gets larger, then our reciprocal value gets smaller. Well, it goes towards 0. Smaller would technically mean it gets like, it keeps going to the negative side, but it keeps getting closer to 0. So it makes sense that it would connect here. And then this approaches 0. But all of these y values are positive. So it will always stay above the x-axis because it won't have a negative reciprocal because you're just dividing 15 by an increasingly larger positive number. Okay, and then in the same logic, this side, right, this is our lowest point on the reciprocal. And then it just gets increasingly, decreasingly, the y value gets smaller, like more negative. So in the same logic, you're dividing 15 by a larger and larger negative number, so it goes towards 0, like that. That also means that we do have a horizontal asymptote right here. And then that should be it. And then before I continue, a vertical asymptote, the graph cannot go through, it cannot touch. because you would literally, if you did go through it, you're saying that there's a coordinate there. That means that it's possible to divide by 0 there, which is impossible. And then a lot of students get that confused with the horizontal asymptote, because you go, wait a minute, I thought you weren't supposed to go through asymptotes. You cannot go through vertical asymptotes. Horizontal asymptotes are there to help like indicate the behavior of the graph at large values of x. So this is 0.5, negative 0.5. You can go through the asymptote as much as you want, the horizontal asymptote, if your x value is not large. This is here to tell you, hey, this graph is going to go towards that line as we get larger x values, or it goes towards that line as we get larger negative values, smaller values of x. Like, this is totally fine. That's not a big value of x. And then 3 marks. Okay. Ew, what the heck is this? Sure. The region enclosed by the curve and the y-axis is rotated through 2 pi radians about the y-axis to form solid revolution. Oh no! Solids of revolution, and we're gonna integrate with respect to y. Okay. So right, this is gonna be spun around to make a 3D like pill shape, I guess. Okay, and then we are going to integrate with respect to y. Yeah, because we're rotating around the y-axis. So the radius is our x value. We're going to integrate from what the heck? What is the top? The top is okay, if at the top here x is 0. Okay, so this is r. Okay, I see. So we're going to integrate from 0 to r. We're going to multiply it by 2, so that gives you the bottom volume, because 0 to r is just the volume of the top part, but it's symmetric. And then what the heck is, what is it, like pi r squared, so then this is f of y. Squared dy, something like this. Yeah, that looks right. Okay, so then we need to find the function in terms of y. Easy enough to do. Y is equal to y to the power of 4 is equal to r to the power of 4 minus x squared. And then am I doing this right? Nope, I am not doing this right. I need to solve for x. X squared would be nice. Oh wow, okay, never mind. They're nice to you. Do I really want to explain volume of revolution, like the concept, so that you guys understand? Sure, why not? Okay, so calculus integrals are about dealing with adding up infinitely small things. So essentially, what you're doing in concept is you're slicing this into very small disks. How do I want to draw this? You're slicing your object into very small disks, that are cylinders. And then essentially, you're just adding up the volume of these to get the total volume of the shape. Now, we know how to find the volume of a cylinder. It's going to be the area of the circle. So the radius, right? And the height here. So area of the circle is pi r squared times the height. The height is infinitely small. So this is an infinitesimal. This is dy. And then the radius, as you saw earlier, the radius is basically the x value of the function. So this turns into an integral from pi x squared dy. And then x squared we need to have in terms of y, which is why I solved for x squared here. So this is x squared, this r to the power 4 minus 4y. And then that's also where this volume of revolution formula comes from. It's literally just the formula for a cylinder. Okay, with that being said, we are gonna substitute our x squared with r to the power 4 minus y to the power 4 dy. Okay, we can pull out the pi, it's a constant. And then we can split the integral. And then do the integral. 2 pi, big bracket. We got r to the power 4, that's just the constant, times y. Evaluated from 0 to r, minus 1 over 5 y to the power of 5, evaluated from 0 to r. Okay, now we just plug in our values using fundamental theorem of calculus. What is this? R to the power of 5 minus 0 minus r to the power of 5 over 5 minus 0. Okay, 2 pi r to the power of 5 minus a fifth of r to the power of 5 is 4/5 of r to the power of 5. This is going to simplify into what? 8 over 5 pi r to the power of 5. Okay, that looks good. Good enough for me. What's my time? 45 minutes. Okay, complex number. Consider this complex number, express it in whatever form that is, Euler form. Okay, so I like to draw. Our complex number is here. Where this is root 3, and then this is negative 3, and then we want to find the argument and the modulus. Should be straightforward. Let's find the argument first. Wait, no, let's find the length. Because the length is just Pythagoras. So what is this? Root 3 squared plus negative 3 squared square root. 3 plus 9. Okay, root 12 is our modulus, I think is the word. And then argument, arctan. Not quite the argument. I'm just gonna do arctan of root 3 over 3. That's 1 over root 3. Oh, this is kind of ugly. And then you should have your special triangles memorized, right? 1, 2, root 3 triangle. So our reference angle is pi over 6. This is pi over 6. And then they want our argument to be here from to pi and to negative pi. So that means that this angle goes that way from 0. So our argument is actually negative pi over 6. Okay, so that means that Z1 in Euler form is root 12 e to the negative I pi over 6. And I guess I see that Z2 is simplified radical, so we'll simplify this one. This is 4 times 3, so 2 times root 3. Okay, that's Z1. Here's Z2. We're going to divide. The cube roots of this are denoted by UVW. Okay, so we're going to cube root the quotient of the 2. So first let's just divide the 2. That's easy enough to do in Euler form. So 2 root 3 e I 5 pi over 6. 2 root 3 e I negative. Okay, Euler form is the best form for multiplying and dividing complex numbers, because when you multiply complex numbers together, essentially their lengths get multiplied together and their angles get added together, and then division would be, of course, dividing their lengths and subtracting their angles or their arguments. So easy peasy, cancel. We're gonna add pi over 6 to 5 pi over 6. So this now becomes literally just e I think that's a full 6 pi over 6, so pi. Okay, now this thing has 3 cube roots, so we're going to cube root this. So when you cube root, then we can just use the Morvis theorem. We divide pi by 3 for our first answer. So u is e I pi over 3. To get the other answers, before we divide by 3, we add full circle 2 pi to the argument of whatever we're cube rooting. So for v, this is going to be well, this is pi plus 2 pi is 3 pi, and then divided by 3 is just pi again. And then for w, we're going to add another 2 pi. So that makes 5 pi. And then 5 pi divided by 3 is 5 pi over 3. Okay, there you go. And then, I don't know, do you want me to explain how this works? De Morvis theorem is literally just what I said about multiplying and dividing, right? Okay, luckily your argument's 1, so we also cube root the 1, so these are all 1. So here, I'll just do this real quick. E is pi over, or sorry, U is pi over 3, right? And it has a length of 1. Now, if we multiply U with another U, we know that we would take the modulus, which is 1. We're going to multiply it by another U. So U times U, or U squared. And then all you're doing is you're just rotating around another pi over 3. And then, of course, if you multiply by another pi over 3, you end up at pi. And this is U cubed, right? And that's exactly what this number is here, right? 1e to the I pi, that's right here, right here. Now, of course, because we just keep going around in circles, there are more ways to end up at pi than just taking pi over 3. That's where you have to consider the other ones. So v, right? A single v is already here at pi. And then, right, if we multiply by v 3 times, we cube it, then we'll end up in the exact same spot. Because if we multiply by v, we go around half a circle, we end up here. This is 2 pi. That's v squared. And then, right, we multiply by another v. You also end up back here in the same position. Yes, your argument's 3 pi, but it is, you know, it's literally in the same spot as pi. And then, of course, 5 pi over 3, same thing. So that's why we have 3 answers. Okay, where am I at? Ugh, almost an hour, and I'm not even at the long ones yet. Okay, there's 2 more short ones, it looks like. No, wait, no, I just did this one. Okay, there's 1 more short one. Ew, this looks like a L'Hopital. Okay, determine the value of the limit. Always see if you can plug in the limit. If we were to plug in the limit, what do we get? We get 0 times 0, 1 minus 1, so 0 over 0. This is indeterminate form, therefore we can use L'Hopital's. L'Hopital's says that the limit of this thing is the same as the limit of the derivative of the numerator divided by the derivative of the denominator. So, okay, let's just do that. The first one's product rule, so sine x plus x cosine x. Okay, divided by the derivative of the bottom, which I think is just sine. Right? Yeah, sure. Okay, and then we try again. So if we were to plug in the value of our limit, what do you get? You get 0 plus 0 over 0. So still indeterminate. And then what that means is that we just do another derivative and we apply another L'Hopital's rule. Because if the limit of this is the same as the limit of that, then we do one more, then the limit of this is the same as that, which is the same as the original. Okay. Bam. Bottom is cosine. The top is cosine. And then another product rule. cosine minus x sine x, I think. Okay, let's plug in 0 and then see what we get. 1 plus 1 minus 0, so 2. There's our limit. Okay, I've reached the long answers. I'm at 1 hour. How many long answers? There should be like 3. Probably 1 is SL, 2 are HL. Sure, let's do this. Let's get this over with. What do we have? We got a sequence. Okay. U1, U2, U3. Consider the case where these 3 terms are arithmetic. Then we need to find the value of k. So arithmetic means that, right, we're adding the same number each time. So they have a common difference. That means, right, that U2 minus U1 is the common difference. And you can take any consecutive 2 terms. So if I take U3 and minus U2, I also get D. So that means that we can make an equation and find out what k is. So let's see. U2 is 3 minus 2k. We're going to subtract U1, which is k minus 5. This is equal to U3, which is 5k plus 3. Subtract U2, 3 minus 2k. And then you see we have an equation for k. We figure out what k is. Okay. Collect like terms. We have 3 plus 5 is 8. Minus 3k is equal to positive 3k. Sure. Okay, so then that means that k is what, 8 over 6? Sure. Answer otherwise, find U3. So now that we have k, we just plug it in. U3. 5 times 8 over 6 plus 3. Great. 40 over 6. Oh, I guess I could have reduced this. Whatever. I'll just do that later. Okay, 3 is 18 over 6. 58 over 6. 329. There you go. 5 marks. It's probably 3 marks and then 2 marks. 2 marks for finding U3, 3 marks for finding K. Okay, consider the case where K is 12. Show that the first 3 terms have a geometric sequence. Okay, easy. Plug in K is 12. Show that they're geometric. So that means that U1 is 12 minus 5, which is 7. U3 is 3 minus 24, negative 21. And then 5k plus 3, so at 63. Okay. And then as you can see, this is geometric because we are multiplying by negative 3 each time. Given that UN is geometric, state a reason why the sum of an infinite number or sequence of terms does not exist. Okay. An infinite sum only exists if R is between 1 and negative 1. Our ratio is negative 3, so the sequence is gonna diverge and, you know, not have an actual sum. Okay, the sequence un is geometric for another value of k, and then we need to show this. Okay, so in the same way, we are going to set up an equation. Of course, this one, we can equate them subtracted because it's a common difference. If it's geometric, when we divide them, we get a common ratio. So u2 divided by u1 is r. u3 divided by u2 is also r, common ratio. Okay, so that means that we have crap, I forget what they are. K minus 5, 3 minus 2k, 3 minus 2k, and like 5k plus 3, maybe? Yeah, okay. So, right, plug it in, and then we just manipulate it, and then you'll end up with our quadratic here. How do we do that? Okay. Multiply this one over here, multiply this one over there, so that we don't have fractions anymore. So 3k minus 2k squared equals 5k plus 3 times k minus 15. No, is it 15? No, it's 5. 5. Okay. Tedious. 9 minus 12k plus 4k squared equal to 5k squared. What the heck? 22k minus 15, I think. And then this, everything goes to the right side. You will get this if I did it properly. Okay. Okay, find the first three terms of the other value of k. So that means that we do need to find the other value of k. Luckily, we have this equation for k, so we can solve it. It's probably factorable. They're probably nice to you, right? 6 and 4? No, 12 and 2. Right, k is 12 or negative 2. This is the one that they told us about, k being 12. So we're going to use the second value of k, negative 2, and then we find the first three terms. So the first one is k minus 5, so negative 7. The second one is 3 minus 2 times negative 2, so 3 plus 4 is 7. And then I'm going to assume that this is negative 7. Again, unless I did my math wrong. Oh my god. Yeah. Yay. Hence write down the value of the sum of the first two m terms for the second value of k. Okay. Why are they doing this to you? Isn't it 0? Okay, you can use the formula, but keep in mind that this is an even number, right? And we know that every pair of the second one is going to sum to 0 because they're just alternating between negative 7 and 7. And we always are adding an even amount because it's 2m. So S2m is 0. Again, you can also just pull out your formula sheet and plug in the values. And then you'll also get 0. wherever it is. Geometric, right? Use this formula, you'll also get 0. But, you know, 2 times m is an even number, right? It doesn't matter what m is, you're multiplying it by 2, it's an even number. Cool. Okay. What is this? Vectors, planes? Almost there, almost there. Okay, what do we got? 4 points, and they make a parallelogram. D is diagonally opposite of B. Find the coordinates of D. Okay, I am going to draw a very simplified version of this because it's going to be in 2 dimensions, but it'll just help me understand. B and D are opposite, so A and C are opposite as well. So here's A, here's C, and then it doesn't really matter where B and D are. B here, D here. Okay, and then we know it's a parallelogram, so this is parallel, and then these are parallel. Okay, find the coordinates of D. Okay, so for this to be parallel, the direction vector from A to B needs to be the same as the direction vector from D to C, or B to A and C to D. So I'm just going to do that. B is -3, -6, and 2. A is 1, -4, and 0. So how do we get from B to A? Looks like we add 4. We add 2. And then we subtract 2. Okay, so then we're going to do the same thing down below with C to D. C is -1, -2, and 4. We are going to add 4, add 2, minus 2. That should get us D. And then I guess I'll write it on one line. So -1 plus 4 is 3, 0, 2. Cool. Okay, the diagonals of the parallelogram ACBD intersect at point E. Find the coordinates of E. Okay, so A, B, C, D. E. Okay, you can do the long way. You would need to find the vector equation of each diagonal, and then you solve it by making them equivalent. Or you can use the fact that it's a parallelogram if this is prior knowledge. If it's a parallelogram, that means that the diagonals intersect at 90 degrees. So if they intersect at 90 degrees, then that means that the vector AC, they're perpendicular, and the vector BD, if we take their dot product, scalar product, it should be 0. That's the quicker way. That's why it's 2 marks. If you were to do it the long way, it would take you more than 2 minutes to do. Okay, so what the heck is AC? AC is 1 minus -1, which is 2, -4 minus -2, which is -2, and then 0 minus 4 is -4. Okay, and then I'm just gonna divide the 2, because I just need the direction vector. So that's the same direction as 1, -1, and -2. This will make my dot product just slightly easier to calculate. And then what BD is next. So B D. So negative 3 minus 3. Negative 6. Negative 6 minus 0. Negative 6. 2 minus 2, 0. Beautiful. Okay, so then this is the same as 1, 1, 0. Wait, how does this find me point E? This is obviously, whoops. Whoops. Oh, do I have to do it the long way? I'm sure there's a shorter way. It's 2 marks, but I spent too much time rambling about this, which doesn't even matter because obviously, like, this won't help you find E. Hey, okay. I guess we'll do it the long way. Shit. Okay, the equation for AC is 1 minus 4, 0 plus lambda of some sort. 1 minus 1 minus 2. This is going to be equivalent to BD. BD is negative 3, negative 6, 2 plus the same lambda? Could be a different lambda. Uh-oh. I told you guys I was rusty. Especially when it comes to, like, later stuff like this. One, 1, 0. Okay, let's see. I'm gonna use the bottom one. Oh, that's kind of, can't see that. So, boo equal to boo. Okay, so negative 2 lambda is equal to 2. Lambda is negative 1. Okay. So now that I know lambda, I can plug it back in and then get my point E. So E is equal to 1 minus 4 and 0 plus or minus my direction vector 1, negative 1, negative 2. Okay, 1 minus 1 is 0. 4 minus negative 1 is negative 3. 0 minus negative 2 is 2. Okay, so here's E. Okay, luckily it wasn't that bad because of this 0 taking out the gamma, the other parameter for BD. All right, so like I said, vector equation, equate them, solve. Once you solve, plug it back in, get the coordinate. Okay, given that AB x AD is this, find the value of M. Okay, do we have A, B, AD? We do. These two. No, AD is this one. I need to find AD. Oh my god. Okay. AB, BA, same thing, whatever. Four, 2, negative 2. AD. Where's my music? Hello? what am I doing? Where's D? 3 minus 1 is 2. 0 minus -4 is 4. 2 minus 0 is 2. Okay, then we cross them. No, I don't want to do the cross product. No. I freaking hate the cross product. Okay, what the heck is this? It's 4 plus 8. -4 minus 8? 16 minus 4? I don't know, just follow the cross product formula. I hate this. 12, -12, 12. Okay, and then I want to find m, so this is a scalar multiple of -1, +1, -1, so -12, that's my m. Sure, it works out. Yay, I think I did that right. Okay, and then hence find the area of the parallelogram ABCD. So this vector product, if you find the magnitude of it, that is the area of the parallelogram between the two vectors AB and AD. So let's see. We got 12. So the area is like 12 times √3, right? 1 squared, 1 squared, 1 squared is 3. Square root it. That's the length of the direction vector, times it by 12. That's the length of the vector product. The length of the vector product is the size of the area of the parallelogram. Cool. Okay, now we have a plane. It's going to contain parallelogram ABCD. Find the Cartesian equation. Cool. So, luckily, we have a normal vector here. So, for those, I guess I'll use blue again. Right, this is A, B. Let's say that this is A, D. Right, this lies in a 3D plane, and then their vector product is the normal vector. Okay, so Cartesian equation of this, you know, is like ax plus by plus cz, and then D is either on the left side or the right side. I don't think it really matters. 0. Okay, so we know what A, B, and C are. Those are the components of our normal vector. D is something that we'll calculate because, again, any coordinate on this plane should satisfy this equation. Right? If I take any coordinate, any point on the plane, they all satisfy this equation. I know 4 coordinates on this plane, so I'm just going to plug them in for our x, y, and z to find our D. So we have A as -1. I'm going to use A. 1, -4 is 0. So let's say that this is A right here. 1, -4, and 0. So x is 1. Okay, plus b, which is the y component of our normal, times our y value of a coordinate, which is the a coordinate, -4. -1 times 0. Again, right, this is my x, y, z. Over here is my a, b, c. And then we need to find out what d is. Plus d equals 0. So d, what the heck is this? 1, 5. Sure, d is 5. Okay. So here is our vector, or sorry, Cartesian equation of our plane. I don't know if they really care that your a value is positive or negative. I forget. If it needs to be positive, then just like flip all the signs, whatever. So this is our plane number 1, because there's going to be a second one. Then we have a second plane. Okay, and then we have an angle between them. Show that this angle, or the cosine of this, is 1/5. Cool. Okay, let me just sketch this. So we have plane 1. Bam, bam, bam. Then we have plane 2. And then they're gonna intersect like that, let's say. And then of course they have an angle between them. And then, you know, just geometrically speaking, they have each of their own normal vectors. Okay, I'm going to draw it disconnected from the plane. But like this is the normal vector for plane 1. And then this is the normal vector for plane 2. And geometrically speaking, it has the same angle as the angle between the planes themselves. And we're going to use these two normal vectors, because we know them, to figure this out. Cosine theta, again, the only two things we can really do with two vectors is take the scalar, well, besides adding and subtracting, is take the scalar product, take the vector product. One of them has cosine in it. Here, this one. So you see? The scalar product is also calculated by taking the length of this times the length of that times cosine. So we're going to do that. Okay, so we know the length of n1. Well, okay. n1 dot n2 is equal to the length of n1 dot the length of n2 times cosine theta. Okay. I need to write all this down. N1. This is -1, 1, -1. Okay, N2. That is the ABC here. ABC. So 5, 1, -7. Okay. I need to find the length of them. This one is √3. No, why are they doing this to me? 25, 49, 50. Okay, √75. Okay, so on the right side, we have √3 times 75. This is cosine theta. And on the left side, we're going to calculate the dot product by multiplying the components together and then adding them up. So we have negative 5 plus 1 plus 7. Wow. So 3 equals okay, and then I'm going to simplify this. 3 times 3 times 25. Okay, so what is this? 9, 3 times 5. Oh, 15, okay. Right, this is 9. 9, root of 9 is 3. The root of 25 is 5. So 3 times 5 is 15. So yeah, we did it. 3 over 15, which is 1 over 5. Oh, we're not done. Shoot. Okay, and then what next? There is a line that goes through E. Oh, I totally forgot about E. That's perpendicular to plane 1. This plane is going to intersect at point F. Cool. Okay, so E is like here in the middle. It's where the diagonals crossed. And then it's going to go, and then it's going to go through our plane at point F. We need to find that. Okay, so first we need an equation for this line. L. Vector equation. Or, yeah, sure. Okay, and then this is point E. So L has a coordinate of E, which is somewhere out here. 0, negative 3, 2. Plus lambda times the direction vector. It is perpendicular to plane number 1. So it has the normal vector, this one, 1, negative 1, 1. Okay, this is going to intersect with plane number 2. So that means that we need to make this equation equal to the equation for plane number 2. Of course, this is in Cartesian and this is in vector, so what we're gonna do is we are going to parametrize x, y, and z in the line. We're gonna plug in x, y, and z parametrized into the plane equation, and then that will do it. So what do we got? We got lambda. We got negative 3 minus lambda. 2 plus lambda. Right, this is our x, y, and z. Okay, this is going to get substituted into the equation for plane number 2, which was this one, 5y minus 7. So 5 lambda minus 7 minus 3 minus lambda minus 7 times z, which is 2 plus lambda equals 1. Okay, solve for lambda. Once we get lambda, you put it back into the equation for the line so that we can get the exact coordinate for f. Okay, 5 lambda plus 7 lambda minus 7. Okay, that's nice. 5 lambda. 21 minus 14. 7 equals 1. I don't know, lambda's negative 6 over 5. Therefore, our coordinate f negative 6 over 5, 3 minus negative 6 over 5, 2 plus negative 6 over 5. Right, I'm just going to use this one. And then clean it up. I hate this. What is this? 15 over 5. 10 over 5. Negative plus 6. Sure, something like that. You get the gist. Time, 1:30. And then I have the last question, 21 marks. Oh my god. Okay, this is a 2-hour video then. I think I'm monetized now, so go watch an ad. Please let me, give me a little bit of money for this. What do we got? Complex number. Such that z minus this, the modulus or the length of it is 3. Show that this. Okay, so z. Okay, so this in itself is its own complex number. Right, and then we want to find the length of this. So we are going to group the real part and imaginary part together. So that's x minus 2. And then minus or plus y minus 1. Okay. Take the length of this. Okay, so that means that we square and add the components. And then this is equal to 9. So instead of square rooting the left side and making it equal to 3, I'm going to keep the left side as it is and then just square the 3. Because we're going to manipulate it and then it'll turn into this. Do I need to do that part? I'm not going to do that part. If you're in HL, you can do that part on your own. You don't need me to show you that it'll be that. Okay. Okay, what do we got? Argument of z minus p, z minus 1 is this. Show this. Okay. Fantastic. Okay, so now I'm doing division, so I'm going to first draw the diagram. We have x and y. And then p is a real number. Okay. So pew. Okay, so this is z plus p, right? Essentially, you're just taking, you're just taking the real part and then you're adding p to it because p is strictly real. Okay, and then this has an argument. And then z minus 1. So maybe like here. And then they're saying that this one, they're essentially saying that this one minus this one is like pi over 4. Yeah, something like that. Of course, this is generalized. I know this doesn't make sense geometrically, but that's because p could be a negative number, and then that would change things. Okay, what do we do? Where's my complex number stuff? I might be stuck, you guys. No, I don't want to do this. Please. I have an idea. Because like I was trying to think of this in Euler form, because like I said earlier, division's best done in Euler form. But I just don't see that happening right now. Okay. We're gonna have to do this the long-ish way. We're gonna have to do division in Cartesian form. Man, what the hell? Okay, division in Cartesian form, you need to multiply by the conjugate. Pew, 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 pew. Okay, so then you get essentially this thing, length of z or whatever. I guess it doesn't matter if it's -1 or +1. And then z plus p times z plus 1. No, why do they do this to you? And then, okay, write this in terms of x and y. So we get x plus p plus iy times x plus 1 plus IY over wait, this is not the conjugate. Oops. Ignore this. Ignore this. I'm being silly. Dude, this is so tedious. 7 marks? Oh my god. They really out here expecting you to do this. Ugh. Okay. Ew. I don't know. There's probably maybe a better way. Probably a better way. Oh shit, this isn't even conjugate. Oh my god. Shit. Okay, let me lock in. Let me lock in. My process is right. I'm just being silly about what the conjugate is. Mother... I wish I could swear, but you know. Unfortunately, I cannot. Because I am a licensed teacher. And if this ever gets back to anyone, I would get in trouble. Because I would swear a lot right now. Okay, so this is Z plus P. And then this is the proper conjugate of the bottom. Stupid. Yeah, screw it, we're gonna keep expanding. Sure, that looks good. Okay, so this is the whatever, and then we know that the argument of this is pi over 4, right? And what is it, imaginary over real? Yeah. Okay. These cancel out. We're going to change this to tan statement. Sorry, there's an alarm in the background. 1. This thing is 1. Multiply this over, and then keep manipulating. You will get to what they want you to show. Probably. Okay, sorry. To recap, right? Write it in terms of x and y, your z. Then you get a proper conjugate, right? Because to do division in Cartesian form, you just multiply by the conjugate. Expand this shit all out. Get the real part and the imaginary part. You could ignore this bottom. This is just a scale factor, right? Take the arctan, imaginary over real. The arctan of that is pi over 4. We change that into a tan statement. So that is also, this statement is equivalent to saying that tan pi over 4 is imaginary over real. Tan pi over 4 is 1. Multiply the denominator over to the other side. Gather all your like terms. You should get this thing. Shit. Stupid me. Okay. Now we have a polynomial. 2 complex roots. Real valued polynomial. They could be conjugates, they could not be conjugates. You don't want to assume that because there's 4 roots in general. So you could have 2 pairs of 2 conjugates, like 4 complex roots. So they may or may not be conjugates of each other. Or you could have 2 real roots and like then they would be conjugates, but we don't know that. Okay, Z1 and Z2 satisfy these conditions here. Use the results from part A and B to find Z1 and Z whatever. Okay, go screw yourself. Okay, hold on. I need to copy these down. Almost there. Okay, let's see. P is 4. Okay, okay. So we got, oh my god. Okay, write this in Cartesian form. Put all of these into both A's and B's. Let's see what we get. Okay, so for Z1, we got x squared plus y squared minus 4x minus 2y minus 4 equals 0. Then we got from the other part B, x squared plus y squared, and then P is 4, so 3x plus 5y minus 4 equals 0. Oh, thank God. Okay, we can we solve for x and y? X is a multiple of y? Okay, well, I'm just gonna subtract these equations, right? And then see what we get. So, pew, pew, pew. This says that x is equal to y. And it would also mean that like A is equal to B. That does not help too much. Oh, oops, I shouldn't use A and B because A and B are already used in the polynomial. Let's use I don't know, VW. What do I do? I mean, I guess I can go and put them back in and then solve for an individual value. This seems a little circular. I don't know if I'll get anywhere with this. But let's see. Okay, if x is y, then I'm going to take equation 1. And let's figure out what x is. This is factorable. 2 and 1. No, not with -2. Ugh. There's no way. At this point in time, they want you to use the quadratic formula. Did I mess something up? Let me just double check and make sure that all my little pieces of math are right. -y. Oops. Ugh, this sucks. Okay, there we go. Right. Wait, yeah. Negative. Stop it. Okay, my bad. This is -x is y. So then this is -x, which makes that +2. So that's -2. This is factorable. Okay, and then like by the same logic, you get the same values for v and w. So like one is like v, like z1 is one of them, z2 is the other one. Okay, so x is 2, y is -2, and then, you know, the other one is the other one, so I'll just say I forget the letters I used. V is -1, W is +1. See, they were not conjugates. Okay, hence find the value of A. Oh, there's no hence. Okay, find the value of A. A is this one, right? Beauty. We did it. Okay, we're going to use Vieta's formulas, so we know what all four roots are because these two roots are two distinct complex roots, which means that both of their conjugates are also roots, so that's all four roots. So we also have this as a root, and then we also have this one as a root, and then right, all four of these you can use Vieta's formulas because this is a real valued polynomial, and that means that A is the negative sum of all the roots because our leading coefficient is 1, and then that ends the video. Let me just double check Vieta's formulas. Yeah, the negative sum. Okay. So A is equal to the negative 2i. I don't know why I know what this is gonna be, but you know what? We're at the end. Let's just do it. Right. The second coefficient is the negative sum of all of our roots. All of our complex number or imaginary parts cancel. So we are left with 2 plus 2 minus 1 minus 1, which is 2. Is that the last question? Am I done? And I'm done. There you go. Overall, not bad. Just a little setback because I was being silly in multiple places on the last question. The rest are straightforward. This was not a difficult exam in any way. Just a little tedious. Yeah. I have paper 2 coming. I don't know when. This took too much out of me. So, I don't know. We'll see when I have time. Thank you for watching. See you guys later.